It's my great pleasure to be here in Warsaw. I've been looking forward to being in this beautiful city. And in addition, there's this fantastic conference. It makes it even better. Thank you, Marek. So just to clarify things, I will be talking about Exascale and the United States Exascale project in the second half of my presentation. But I'm no longer the director of that project in the United States. I've found in my career that usually if I start something new, the first 2 years are very intense, and then it's time for me to turn it over to somebody else. So when I agreed to be the founding director, I said, I'll do it for 2 years. And so Doug, who is at Oak Ridge National Laboratory, is now the director. And much of my talk will also be a little bit philosophical and retrospective because, when people get to be as old as I am, we tend to talk that way. So please be patient with me if I reminisce a little bit and try to get lessons from history. Now, a little bit about Argonne, just a little bit in case people are not familiar with it. It's one of 17 national laboratories of the Department of Energy. It's outside of Chicago, about 40 kilometers southwest. And it was moved there because it started out as an effort in the University of Chicago doing the first controlled nuclear fission. And it was thought that being in the center of a big city was not the best location for that type of research. Now, two things I wanted to mention. You see labels on the campus. One is the advanced photon source. So that's a traditional accelerator type thing, X-rays. So it's an international user facility. Then towards the bottom right, there's the Theory and Computing Sciences building where there's another international user facility which has to do with computing. And so that facility, companion to the one at Oak Ridge, is considered at the same level as a particle accelerator as a way to do science of many kinds. So to me, when about 18 years ago, the term user facility was applied to big computing resources, that was a sign of maturation to me that it's no longer just individuals essentially playing with computers. Now, as an aside, the other thing I wanted to mention is Chicago is the city in the world that has the most people that are Polish, except for Warsaw. It's very heavily influenced, and in fact, there's a wonderful statue of Copernicus by one of the museums outside, as well as several others around the city. So Chicago has a lot of Polish heritage. Now, I'm not from Chicago, but I have lived there for a number of years. So Argonne National Laboratory was, based on work by Enrico Fermi and Arthur Compton, which did the first controlled nuclear reaction under the stands of a football stadium. And so this is a drawing that was made at the time. People didn't have smartphones, so they couldn't take videos. Now, when this was done, people were very concerned about, is it safe to do this? And computing came into play. So Enrico Fermi did some calculations, and they were convincing enough that Arthur Compton said, okay, we can do it, and we probably won't all die and make a tragedy in the city of Chicago. So this was in 1942. So, of course, what they used was calculators, but good mathematics, good mathematical models, enough to take this risk. Because at that time, people really didn't know if this reaction would run away and destroy much of the planet. Okay. Now, I have many slides, but I can summarize them in 2 words. It's just like the movie The Graduate. There was one word, plastics. Well, this is 2 words. I'm verbose. So integration and perseverance, to me, are the key to success in advancing computing, and most importantly, in taking advantage of computing to advance science, engineering, and society. So integration of what? Well, to do computational science, you need to do many things. You have to develop codes. You have to have the mathematics and computer science research. And you have to do it in collaboration with the people who have problems to solve. Training and workforce development is essential. If you don't have the people with the right skills, it's difficult or impossible to make progress. And then the facilities that are such that they enable things you couldn't do before, and they're open to many people, broadly available. Of course, networks to connect them. And then because in our field, very high-end, high-performance computing, there isn't a big enough market for companies to really make a lot of money. One has to partner with vendors, provide incentives for vendors to keep advancing the state-of-the-art of the systems. So architecture, software, and so on. And then also collaborating with not computer industry, but what I would call end-user industry, automobile companies, airplane companies that need this kind of computing, and collaborating with them because they usually will not buy their own huge computers, or at least not until they've demonstrated that those huge computers will make enough of a difference. And there are examples of that. One that I'm aware of for certain is Proctor & Gamble company, which makes detergents, soaps, many products for the house. They first started using computing facilities at Los Alamos, at Argonne, at Oak Ridge. And then somebody in Procter & Gamble was able to convince the board of directors to buy quite a sizable computer to install in Procter & Gamble because they saw that the advantages were there, that the cost-benefit analysis was there. But it would not have happened if they hadn't been able to do the demonstrations. Perseverance. Well, even in this conference, I've heard a little bit, a few people say, things go fast, there are quick uptake of things. And that can happen. Certainly smartphones were taken up rather quickly. But in our field, usually things take a very long time. At the architecture level, very long instruction word architectures, very good idea. I programmed systems like that in the 80s and early 90s. But in terms of being widely adopted, it took many years. Message passing libraries, as was pointed out on the first day, and I'll say a little bit more about it later. There were several efforts to converge on those. It took over a dozen years to come up with what is called MPI. The idea of cloud computing really started in 1990. It took a long time to mature to that level. Same thing with big data. And then even applications or methods. Lattice QCD has been derided for wasting a lot of computing time because it takes each factor of 10 or 100 more computing only improves the statistics a little bit. But if you keep on doing this for 4 decades, then actually it's become useful. So lattice QCD has become quite important for both designing new accelerator facilities and then understanding what experiments to do and how to interpret the results of experiments. So lattice QCD for a very specialized audience, I admit, is now no longer a waste of time, although I still hear people say that it's not worth the amount of computing they do, but they're really getting to fundamental issues in physics. Artificial intelligence, well, everybody knows that started in the early 60s, or by some measure the 50s, and it was always 30 years away, but no longer. Now it's difficult to pick up anything to do with computing that doesn't mention AI as the solution to everything. And even NVRAM, non-volatile memory, seems like a new thing, but 1992 was a few years away. So does that mean that everything that's pursued for a long time will be successful? Of course not. But if you believe that something really is going to be valuable, be patient, persevere, and then hope that you can find funding sources, program managers somewhere in your government that will also understand that even though computing is thought of as evolving very quickly, computational science typically does not evolve that quickly. And the reasons for that are software. Software is complicated as part of infrastructure. Even if you have a wonderful idea for a new language, it's very difficult, sometimes impossible to get it adopted. And it's because people rely on a certain aspect of software as part of their ecosystem. Application codes certainly have lifetimes of decades, and you don't just throw them away, although in some cases they do, after say 20 years, decide it's time to rethink and re-implement. And that has happened in a number of cases, especially in chemistry. And even things when an individual might be the one doing the work initially, and so there's very little coordination time lost, but then if it's going to have a lasting value, you end up having to have a small company or a group that grows and grows, because software is infrastructure. It's not just something that you use and throw away. And to do computational science, you also have to have very broad expertise. So, people have to not only be good at, say, physics, material science, chemistry, but to do it, you have to understand the architectures, the mathematical models that are appropriate, the algorithms that are relevant to both the mathematical model and the architecture you're going to go on, know how to program efficiently, understand the architecture of the software, debugging, and so on. I don't need to read all this, but it's a complex situation. And therefore, usually these days you have teams of 5 to 30 people working on one code because there are so many aspects to it. Seymour Cray said more than once, anyone can build a fast CPU. The trick is to build a fast system. Well, when I first heard Seymour talk in 1976, in fact, he spent almost no time on those beautiful vector units that he had designed for the Cray 1 Serial 1, but he talked more about getting data in and out, and also the cooling. So the corollary to me of that obvious theorem is to make fast systems usable. Once you've got a fast system, you have to create an ecosystem around them, which includes the people, the software, the hardware, the vendor community, and the user community. So here's one example, and there are many, of an application that exemplifies a lot of the ecosystem that it uses. This is Jackie Chen from Sandia National Laboratories, Livermore. And so, and she is part of the Exascale Computing project. So what is she doing? So she's doing combustion, trying to do more efficient engines. And so let me point to, I guess, this one. So she's using, results of an institute that developed FastBid, Adios.io. We have somebody here that has something to do with Adios. So that's something in addition to the chemistry going on. Visualization to understand what's going on, doing it in situ, and particle visualization. Then a new task-oriented programming language, adaptive mesh refinement, in situ a joint uncertainty quantification analysis workflow. The code Pele using adaptive mesh refinement codes, multiphysics, geometry. So just this one code has to bring in many different parts of the ecosystem to be successful. And it's still a work in progress. So let's go back in history a little bit. Peter Lax was asked to head a committee in the early 1980s, wrote a report in 1982 known as the LAX report. And if you read it today, I believe that it would sound like excellent advice for today. So here's a snapshot of it. They recommend a program that provides increased access through high bandwidth networks. This is 1982, remember? To adequate and regularly updated supercomputing facilities and experimental computers. Increased research in computational mathematics, software algorithms, training of personnel, and research and development basic to the design and implementation of new supercomputer systems and increased capability. So you could take this, and this is what you need to do today. And I did not change any words, as you can see. I took a snapshot. I have a few copies of this report. Of course, to implement those at that time in 1982 was made more difficult because parallelism was starting to be talking about and pursued. Now, the ILIAC 4 preceded that. That was mid-70s. But then Los Alamos was building a system they called PUPS, where the U is a mu, the Denelcor HIP, and then some experimental ones. So that meant that people had to deal with a new programming paradigm. Now, I will talk a little bit about 3 of the elements of the ecosystem that I feel are often not talked about as much as they might be. We tend to talk about architectures. So one is mathematics, the other is software libraries, and the third is the facilities themselves. Okay, so I confess my PhD is in mathematics, so I'm slightly biased here. But mathematics really is central to the ecosystem because you use mathematical models in many cases, not all. And then you have to worry about how to approximate, how to discretize, how to write solvers. And there are mathematical questions associated with those. It's not a matter of just tinkering with a program. And so a major contribution of mathematics to HPC has been resolving the questions of the mathematical nature of those. And it isn't all numerical calculation. There's a branch of math called applied analysis that doesn't do numerical work, but it does analysis non-numerically. So you're formulating the mathematical models and understanding the properties of their solutions. Is the model complete? In other words, does it have a solution? Are there multiple solutions? And what are the properties? And often simplifying the model by reducing its dimensionality. Very often the mathematical model is too complicated to be tractable for a rigorous mathematical analysis. But then you can do asymptotic analysis and perturbations. If it's a singular perturbation, the kind that is a variable goes either to 0 or to infinity, depending on how you formulate it. The nature of the partial differential equation changes. If it was parabolic, it can become elliptic or hyperbolic. And so by doing the asymptotic analysis, then you can get to something that you might treat numerically. My PhD dissertation was, in fact, to do that for an equation in magnetohydrodynamics. Then there is computational mathematics, of course, and we're more familiar with that, so I won't spend any time on it, but I wanted to remind people that even non-computational mathematics has had and will continue to have a role. It's just we don't usually talk about it. It's had a lot of impact, and as has been pointed out in this conference, mathematics is very relevant to artificial intelligence and data analysis as well. And in fact, that's become a very active subset of mathematics research. So here's one case study by Phil Colella that brings in a lot of the elements of the ecosystem again. So it started out with applied analysis, asymptotics for reacting fluid flows in the late 1980s. and then had to develop new discretization methods, listed here, multi-grid solvers for elliptic parabolic PDEs on adaptive mesh refinement grids, and doing this for decades. And by the early 2000s, people were combining those components to simulate laboratory scale combustion and being able to compare to experiments. And that approach is also used to simulate type 1a supernova. So, this is a second example of how the ecosystem is essential to solving problems like this. Now, software libraries programming models are more familiar. So I quoted the LAX report, 1982. Here I'm quoting a book from 1993, 11 years later. And so what were the recommendations for system software and tools? Getting a support environment for parallel computing, standards for parallel I/O, because quickly I/O became even more difficult, standard for message passing on distributed memory machines. And so it identified the greatest single hindrance to significant penetration of massively parallel processing technology in scientific computing is the absence of common programming interfaces across various parallel computing systems. Again, I will reveal a bias. The PACs were developed most of the time at Argonne National Laboratory. When I spent several periods at Argonne. My first one, the week that I arrived was the week that ISPAC was being released, eigenanalysis software. So the PACs, again, over many decades have been developed, evolving. And I still run into people sometimes that say, well, those mathematical libraries like the PACs are just a toy. Real applications don't use them. Well, it turns out that often they do, but they integrate them. And in terms of leverage, LAPAC is used by at least 13 hardware vendors in their libraries, so it's buried, which is fine so long as they're being used, and used by at least 17 software companies. So they are being used, although the user may not be aware that they even exist. And a good friend and colleague, Cleve Moeller, who developed MATLAB, I talked to him recently in the context of a project that I was doing, and he gave me this quote, verbatim. LINPACK and ISPAC spawned MATLAB because he was spending his summers at Argonne at that time, and he participated in those. And today, and this was from last fall, MATLAB has millions of users worldwide. MathWorks has over 4,000 employees in at least a dozen countries, $1 billion this year. And of course now MATLAB uses LAPAC instead of LINPACK and ISPAC. So again, the leverage, the benefits of these libraries are real. So next time somebody tells you don't bother with those libraries, you might say, well, I'm not sure I agree with you. Message passing libraries, well, there are people here who were very involved in this. So most of you know the story, but there was no standard for message passing, even though the distributed memory systems were the ones that were getting a lot of traction. And the vendors themselves in the mid-'80s, there were 4 or 5 companies already, tried to self-organize to agree on a standard, and that didn't work. Around 1989, 1990, there was an effort led primarily in Europe, which again tried, but somehow didn't quite make it, but obviously it eventually did have the maturation. So the research began on 2 areas. One, developing portable message passing library based on the de facto usage that already existed with the vendor libraries. But then the more important is what functionality and features should be available, not just what already was available. So as is often the case in software standards these days, it isn't codifying what's in use, but also figuring out what should be added to make them better. And so the MPI forum made that happen. Now, for a long time, Cleve Moeller and MathWorks resisted going to a parallel version of MATLAB. But eventually, they decided, okay, the time has come. And one thing that really made it feasible and had a huge influence, again, was the existence of MPI. And one reason for the rapid uptake of MPI for actual use is that as the standard was being developed, MPICH was being developed, which guaranteed that the features could actually be implemented, that they would work together. And so all the computer companies just sucked it up. And there are still collaborations going on with the MPICH group and several of the companies because it's mutual benefit to work together. And it does have a lot of impact. Okay, so let's go another 10 years. 2003, the National Science Foundation commissioned the Blue Ribbon Advisory Panel on cyber infrastructure, one of these words that makes it sound exciting and special, right? So what were the recommendations? So here, I was part of this advisory panel. You know, what we're pushing is that it's really time to think of the computing environment more broadly and stop emphasizing only floating point calculations and the classical mathematical model solution. But let's think about how to get people to work together, data, information, as opposed to data, tools, instruments that both operate at the high levels of computational, but also storage and data transfer capacity, to create, again, an ecosystem that was broader, that would conform with the needs of scientific research. And of course, we emphasize that human resources are critical to making cyber infrastructure and applications work. The recommendation was to do 4 things, just like the Peter Lax report, right? Fundamental research on the cyber infrastructure itself, research on how to apply it, acquiring and developing production quality software, and then facilities. Okay, what about facilities? Well, to me, especially in the context of integration, they're absolutely a key element of the high-performance computing ecosystem. They're the setting for interacting with the hardware and software architects, the computer vendors, the system operators, and the users. That's where you can do a full-scale test of the hardware, system, software, I/O, storage, tools, and how well they're integrated. And they also provide access not just to the system, but in all the cases that I'm aware of the very high-end facilities, they have in-house teams of experts for performance analysis, for which algorithms to use, how to use the system efficiently. Access to those people through the facilities is also a key element. It's, obviously there are facilities, those facilities are scientific enablers because it isn't just the big computers. They have software, often a lot of codes that are widely used. You have to worry about where to cite them, how to cite them, power, cooling, and so on. Again, the people who understand tools, computing, science methods, and you can bring all those to bear on big problems. They also provide the setting for collaborating with the vendors, various institutions and agencies. So again, you can integrate research and production. And there are many examples where through facilities, then companies evolved their products. In one case, Intel, did the Intel Touchstone Delta around 1991. That led to the product called the Intel Paragon. Sandia did a research version a little bit similar to that, Red Storm, and that became the Cray XT line of computers. And there are many other examples of that. So, and of course, they're critically important to maintaining a path to funding for important ideas because it's easier for people to grasp facilities than just a mathematical equation. It's just a fact of life. And you can have long-term relationships with the vendors, but that doesn't mean that you ignore other possibilities. Networks are obviously important, and these days interconnections globally of various networks. So having that available, we can take a little bit for granted, but without them, we wouldn't have the world that we have today in terms of computational science, much less Googling to find out who wrote a book. And the obvious, I'm preaching to knowledgeable people here, data and simulation are intertwined. Sometimes you only do data, sometimes you only do simulation, but more and more often both are involved. Okay, so I was supposed to talk about exascale computing, so I think I'll do that now. First, a reminder that starting in 2007 in the United States, there was an effort to first identify what would be the benefits of exascale computing. And so this was done in the usual fashion. You organize workshops. So I was involved in organizing 10 workshops that produced the reports. They're still available online. There's I checked this a few days ago, so I hope it's still working, that URL. And so they were, on climate science, materials, chemistry, biology, all kinds of fields. And the idea was, I think appropriately, let's first identify what the benefits would be. And when it says advances enabled by exascale and beyond, it's because in some fields of physics, the calculations indicated you needed more than exascale to address certain problems. Okay, so to me, so I've been involved in some fashion or the other in exascale in the United States for a few years, and again, I simplify it as the biggest challenge, and there are many, many technical challenges, is creating an enduring exascale computing ecosystem. And I put in bold the people with the expertise to develop, maintain, and use the ecosystem as a key part of that ecosystem, but I've been talking so far about different aspects of it. And as usual, like with a chain, the weakest link is the one to worry about. All aspects must be strong if the ecosystem is to function effectively. So ecosystem really means integration. So the Exascale Computing Project of the United States is an R&D project funded by the Department of Energy. And there was choice made that that particular department would take the lead, but it collaborates with NASA and NSF and other parts of the government to ensure all the necessary pieces are in place to deliver the first capable exascale ecosystem, including applications, an integrated software stack, advanced computing system engineering, and hardware components. And capable exascale computing means that for the hardware, at least 2 architectures, and that the power of the hardware is measured by applications as a ratio of how well they run on 20 petaflop systems and 200 petaflop systems that are more recently available, as opposed to a LIMPAC number. Software has to be a software stack that can be widely used, not just specialized for, say, lattice QCD only. And then at the same time, having applications as part of the ecosystem, not just as users once the ecosystem is developed. The organization is a little bit complicated. The main point I want to make here is that the project is what I will be describing in a little bit of detail, not very deep this time, but the Exascale Computing Initiative of the United States has 3 parts. So there's a project, and then some other parts of Department of Energy and other agencies are developing applications with separate funding. Now, there's coordination and collaboration, but it's not part of the project, because project is a very formal thing here. And then The buying and operating the systems, the pre-exascale and exascale, is done by the existing facilities with separate money. And that's the way it should be, because the project will end. It's a 7-year project, but the facilities have been there for decades. They will be there. And that's how you know if what's being developed is really useful for production. So that's a slight complication in explaining it. So the project itself, at the bottom you'll see project management, because it's a big complicated project, and so you really have to have formal milestones and risk assessments and so on. But then more interesting to us typically would be the top 3 things. Hardware and integration as defined in this project. I'll give a little bit more detail. Software technology and application development. So just to give you an idea of the scale and complexity, it's a 7-year project, approximately $1.7 billion. And this is the R&D, again, not computing hardware. There are 6 of the 17 national laboratories involved, but 16 of the 17, the 6 are essentially managing the project collaboratively. But the R&D is being done at 16 of the 17 national laboratories. And so there are about 100 teams doing various things, and about 1,000 researchers. Again, it's a big, fairly complicated project. Now, one thing that I think is particularly nice is involving industry. So there's an industry council, which is not computer companies. Now, there are several software companies in this list here on this slide, but not computer companies. So these are companies that believe they need or will need exascale, and we want them to periodically be briefed on what the project is doing and give us advice on whether the direction we're going in is a good one for them as far as they can determine now. So unless it's changed, we meet every 6 months, and it's a very productive meeting in my experience. And you can see a wide variety of companies. You could expect General Electric, General Motors, Boeing, but what about DreamWorks? Well, of course, these days movies, although I very seldom see them, are primarily special effects, and so they need a lot of computing. And in fact, they use particle and cell methods, to simulate some of the phenomena that they show, such as melting ice. So they're really trying to do things nicely. And then I already talked about Procter & Gamble. Fedex is a company that you might not have expected there, but in their case, they're like DHL, so they deliver many millions of packages. And one of their hubs is in Memphis, Tennessee. And what if there's a forecast for thunderstorms in Memphis, and so in the middle of the night, very quickly, so it's a time-dependent thing, within an hour or two, they need to do a new graph analysis and reroute all the planes and figure out how to end the trucks. So it's not sustained simulation, but it's really graph analytics on a short time scale for a rather large problem. Okay, I could go on. It's just one of the features of the project that I think is particularly nice. And this very busy slide, I'll just say a couple of things about. So the 3 major parts of the project are application development, which has many parts to it, hardware integration, and software technology. But they have to interact among themselves. So those 2 interact, these 2 interact, these 2 interact. And then what's in the middle? Well, the software stack, access to the facility, training and productivity is where things meet, because integration is critical to success. So what's in application development? Well, mostly applications, but also co-design centers. So the applications are binned in 6 areas: national security, so nuclear weapons largely, energy security, economic security, scientific discovery, Earth system, and healthcare. Now let's look under energy security. Well, So there's an application on wind plant turbine efficiency, another on high efficiency combustion engine design, subsurface use for carbon capture, biofuel catalyst design, that type of thing. So each is a pretty complicated application and rather challenging, and each of them has a team preparing an application to run as soon as, on exascale systems as soon as they're available, but working with the software people and the hardware and integration people. And then co-design centers here, a little bit different definition than one usually uses, but nevertheless, that's what it was. That's what was decided on. And so you can see CODAR, co-design center is the interactions of applications, data analysis, and data reduction. COPA is numerical recipe for particle-based methods. AMREX, block structured adaptive mesh refinement algorithms and software, of course. C, discretization software, graph algorithms, machine learning methods, and then a special on proxy applications to improve the quality of proxy applications. So some of the mathematics that I subjected you to earlier in this talk is being pursued here. Software technology, programming models and runtimes, development tools, mathematical libraries, data visualization, and software ecosystem and delivery. 89 products underway at this point, and an attempt to make sure that the software developed can be more easily integrated into applications and into the ecosystem, software development kits. Sorry, I thought I had a different slide coming here. Oh, yeah, this slide. Must have flipped them somehow. So, and there are versions of many of those 89 projects, products available in GitHub, and so that gives you a feel. Of course, they're not exascale because we don't have exascale systems yet, but you develop in steps, and so there are things that are available for pre-exascale now. In terms of highlights, it's a project, so we have milestones. I won't give you the formal definition of milestones, but PAPI, which I think most of you would be familiar with, for performance analysis tools, is working with a big chemistry project, NWChemX. That's one of the 25 applications, and so they co-designed, with the team, software-defined event-enabling instrumentation of an algorithm. Legion is a new programming language that I mentioned early on that Jackie Chen is using, and a few others are starting to use. Adios is, of course, the I/O, and it's working with a number of codes to help them do I/O. Slate is a higher level than LAPACK and ScalaPack, and so it provides an API so people can call on Slate, which then will call on GPU specific versions of LAPACK and so on. Hardware and integration, so it's a little bit different again from what you might expect, because again we don't buy hardware with the project, but the hardware is being bought by the facilities, and the facilities are the ones that decide, do we install this crazy software that the project is developing? And so it's not wise to wait until the exascale systems are on the floor and then say, here, take this. So we're working with them now, the facilities, to say, this is what we're developing. Let's see if you agree that if we deliver the software in this fashion, that you can more easily install it and maintain it, and help us maintain it, and also that it's software that you're willing to run, that you feel it won't be crashing the system, for example. One part of it, the hardware part that isn't buying machines, but it's buying technology essentially, was contracts to 6 computer companies that were put in place a couple of years ago. Say here, this is based on a competition where we asked companies to propose specific technology advances maybe it's better memory, or maybe it's a better interconnect, that type of thing. And so 6 companies won contracts for substantial amounts of money, and each of them is putting in at least as much money. So what are the companies? Let's see if my old brain still works. Probably not, but let's see. IBM, Intel, NVIDIA, AMD, Cray, Hewlett-Packard, 6. I did remember all 6. And some of them have subcontracts. So that is very important to both motivate many companies to stay involved at the high level, high performance computing, and also risk mitigation, to make sure that there are several. And everything that they propose, the idea is that they would be features that could be put into a real product, not just a demonstration for research. So that's an important part. And then you have to have a team that evaluates the hardware technology and performance. And I already mentioned the software deployment and application integration at the facilities. And then the community training and productivity tools is also part of this subset of the project. Now, in terms of systems, the ones that are relevant to the project, and it's phrased this way because there might be pre-exascale and exascale systems in other parts of the United States that are not associated with the project. So, lots of pre-exascale systems. The most recent, of course, are Summit and Sierra. And then what's coming, the plan is to have in the 2021 to 2024 era, one at Argonne, one at Oak Ridge, and one at Livermore. Possibly phased like this, but that could change. And this one, could be straddling. As Los Alamos and Sandia jointly have a facility there. So obviously, having these pre-exascale systems, especially the most recent 2, is very important. Summit, I'm sure you've probably read a lot about it, but just a quick snapshot. It's 200 petaflops peak. Consumes only 13 megawatts. It's not too bad. 250 petabyte file system, transfer at 2.5 terabytes per second, and you can see how powerful each node is because there are only 4,600 nodes. Sierra is very similar, but there are some differences. The nodes are configured differently. There are only 4 NVIDIA GPUs on the Livermore version instead of 6, for example. Use a little bit less energy. Peak is only 125 petaflops because it has a lot fewer GPUs. But for their needs, it's probably configured a little bit better. So now, good. I haven't run over time yet. So what are common challenges that applications face? Porting to accelerator-based architectures of various kinds. Exposing additional parallelism because there's so much to be used if you're going to get good performance. Coupling for new multiphysics. A lot of them are multiphysics. New mathematical approaches, algorithmic improvements, and leveraging optimized libraries. So how are some of these challenges being met? Well, one of the co-design centers I mentioned earlier is Center for Efficient Exascale Discretizations. So they want to develop algorithms and software to make things more efficient. So their approach is performance-enabling math foundation. Yay for math, right? Fast kernels, benchmarks, integration, through a high-level API, NAC 5000 SCFE code, the low-level APIs, and having close engagement with the applications, with people who are tasked to work together between the co-design center and the application and so on. So high order software ecosystem is being developed, and they're working with a lot of applications. Not all 25, but a pretty good subset. You know, and these are some of the codes and applications. So one is the modular nuclear reactors, for example. Additive manufacturing, very different. Wind energy, very different. I've talked a fair amount about the adaptive mesh refinement co-design and the co-design center, so I won't say too much other than you know, that it is, again, working with many applications, and you know, combustion, multi-phase flows, cosmology, astrophysics, and accelerators, where accelerators here is particle accelerators, you know, big physics facilities, not GPUs, okay, overuse of the word. Now, to me, the exciting thing is that all 5 of those projects had their own in-house developed version of adaptive mesh refinement, but now as part of the project, those 5 have decided they're going to use the results of the co-design center on AMR, and so that means that they have less work to do and probably will get a higher quality product, because these are people in the co-design center who've been working on AMR for 30 years, and then they can, you know, also benefit by providing information. This is what I need that you don't yet have. So that's, to me, is a big success story. And you know, one of the co-design centers I wanted to emphasize has to do with data analysis and data reduction. I'll say no more about it in the interest of time. A new one is for machine learning co-design, and this is a relatively new area. So you know, the requirements are not as well analyzed and characterized as in some other areas, but one has to start somewhere. So this is a start, and so they want to produce a tool set that will have these features. So one more example, you know, for the wind plant simulations, and the point I wanted to make here is they're leveraging optimized libraries for computational fluid dynamics solutions in ExaWind. So these are, again, farms of wind turbines, and the idea is how to position them, because you can make a big difference depending on how they're positioned. Big meaning, you know, 20, perhaps even 30% more energy produced with the same number of turbines. And so Hyper and Trilinus are among the software libraries for numerical calculations that are being evolved by this project. They existed long before the project, but now they're being evolved so that they'll be available and efficient for exascale systems. And so the wind project is now incorporating elements of those 2 libraries. Okay, so this is having ended with a wind turbine application. I'll say this is the end of a whirlwind tour of the Exascale computing project. I mean, normally I would have dedicated the entire hour to it, but I felt that I wanted to convey the messages of integration and perseverance, and to do that by going back in history a little bit, 40 years or so. Now you can get a lot more information online, which is one reason I don't feel too bad about not having spent my entire time on the ECP, because you can get all the latest there. Now I have, I believe, 5 more minutes. Is that correct? Let me show you something for amusement. This has to do with the speed of evolution. So here's a reproduction of the Wright brothers flyer. So when was this developed? 1903, right? And if you look at it, you can see that the pilot would be lying down here. These are the rudders. You know, sort of a strange looking thing, right? Now, 10 years later, this airplane was available and working and going 126 miles an hour. In only 10 years, you go from something that could fly 100 meters or so, something like that, very slowly, to this. Now, to me, this is fast evolution. You can see there's a cockpit. I mean, the plane looks like today's planes in only 10 years. So, here's an example of a technology that really did develop a lot faster than computing. So we shouldn't, I'm joking, of course, so we shouldn't brag too much about how quickly computing evolves. Airplane design, I feel, evolved much faster. Thank you for your attention.
We have got time for some questions, please. I'd like to ask. Yes, please.
Thank you for a very exciting talk. I have such question. You've mentioned that the key word is, one of the key words is ecosystem, and so you explained what it is. Now if we look globally, so we know you describe how it looks in States, then in Europe, we have Euro HPC, we have PRAISE, alike initiatives. So do you see in the future even more integration between initiatives in the area of supercomputing across the globe, so in US and in Europe, that somewhat there will be more collaboration, so maybe, let's say, less centers, but more emphasis on training people and hardware being the less important thing where it lies. So I don't know, do you understand my question? But
well,
yeah.
let me try to, I'll provide an answer and then you can tell me if I understood it. The first part of your question, I think, has to do with international collaboration on computing. Let's not even talk about exascale because that's a temporary thing. So traditionally, there has been collaboration, some of it formal, some of it informal, as happens in science. I personally am very much in favor of collaborations, with the right people. And the right people are often in different countries, in different world regions. In the 1970s, when I was at Argonne leading a division in math and computer science, we had a formal joint project with Russia, with Moscow State University, with Voivodin, on developing some numerical software. And this was at a time when relationships between the U.S. and Russia were not so good at the political level, but at the scientific level, it was a good project. So I'm definitely in favor of those. Some years ago, much more recently, the United States and Japan entered into a formal collaboration on, I don't remember if it was called HPC or exascale computing, but in any case, we have people who spend several months in Tokyo or at Tsukuba, and then Japanese who come and spend time at Argonne, among other places. So those things can happen, and I think should happen, because there's good work going on, good people all over. Now, in terms of one thing you said, fewer centers and more on training. There I would not agree. I would say more centers and more training. Because centers really matter. It's not that you can look at the hardware, but it's because where you have this environment for the integration, the stimulation of ideas. So centers do R&D. For example, they have to manage these complex systems, and so they often develop tools to understand what's going on in their system, how users are using it, what the bottlenecks are for scheduling jobs or I/O. So I think not necessarily having a lot of the highest end systems, but many pretty good sized systems, because they have this ecosystem that involves people and methods. Training, I certainly think is very important. The gains in productivity that a person can achieve by getting the training are huge and long-lasting, and unfortunately, there has been a tendency that you assign a graduate student to develop part of a code. So the graduate student has, the incentive to finish the PhD, and no time to look at what's already been done, perhaps, no encouragement to do that, maybe no formal courses on, I'll say, high-end computational science at her university, and so the incentives are not right. So there are some programs that have special fellowships specifically aimed at that. That you're getting a PhD, you get this fellowship, and in return, you have to take some courses to make you a computational scientist and not just a chemist, for example, or a nuclear physicist. So that would be one example of a way to do it. So I'm not talking about 1-week courses. I'm talking about academic courses, which can be supplemented by 1-week ones, but with real incentives, because otherwise it won't happen. So I agree on the training, investing in that, but I think having more facilities that are full spectrum facilities, are not just installing hardware and saying here it is, that's a good way, and it also provides the on-the-job training opportunity. Because let's face it, most of us over the last few decades, I'll speak for myself, I initially taught myself how to program because it was so long ago they were still using Abacus. Yeah.
You answered my question, if I may, but it triggered another one, but the short one then. So we knew what happened to nuclear physics in States. So now we have facilities like CERN, then we have high energy physics. We know what is happening to Phoenix experiment. Now we have at LHC the center. Now Chinese are talking about building one. So the follow-up question is how you see in 10 or 20 years from now, will there still be funding actually for having this kind of multiple exascale or whatever will come after these centers worldwide? Thank you.
Well, I think there will be such funding. Science is sort of a never-ending frontier, and more, science requires simulation and data analysis. So I think the funding will continue because it will probably be increasingly obvious of the benefits to society. I'm an optimist, and I do think that we can help society in many ways.
Thank you very much. Another question.
Paul, could you please give your own perspective on, in the last 5, maybe 10 years, what was the most profound new discovery in the field of mathematics that was most impactful to computational science?
Oh boy, that's a difficult one, America. I don't have an answer for you. Partly because, although I did start out as a mathematician, the last 10 years I've been focusing so heavily on computational science and then exascale computing. If you had asked me for a longer term, I would have said maybe Leslie Greengard's work on the many-body problem. I felt that was a game changer, and that was mathematics. Longer ago than that, depending on how you want to measure it, what we call the fast Fourier transform, which we think of as 1966 paper, but or 65 rather. But of course, it was really done by Gauss a little bit earlier. So there are a few methods like that. Certainly, so I in the last 10 years or so, I can't really identify one, but things like the use of spectral methods. But again, that's not in the last 10 years. Really make a big difference.
Just a moment. Other questions,
yeah.
please.
Yeah.
Other questions, please.
Oh.
Or comments?
Yeah.
Yes, please, Professor
Yeah.
Lessing.
Information is this area of mathematics which really will influence future computing capabilities.
Yep.
Would you like to repeat, probably?
Sorry.
Well,
I'm sorry, I didn't. Was there a question or
your
a comment?
question or comment? Yes, your comment, please.
Okay. No, I think that simply quantum information is this part of mathematics and theoretical physics which really will influence future computing capabilities.
Yes, I would agree with that. There, there's physics and mathematics involved there. Are you familiar with Paul Benioff's work? I mean, this goes back to the 1970s. I mean, I provided support for Paul for a while to do that because I felt it had potential to impact things. Yeah, and then certainly there are mathematical questions there.
Thank you. Other questions, other comments? Please, yes.
Yeah, I guess the last, only 4 or 5 years, you see a lot of impact from statistics, right? Because that's what in a form of glorified statistics these days we call AI, right? It's really heavily relied on the branch of mathematics, where it looks at different types of statistical methods. And I think the work in the next few years, looking at how to solve the black box problem or understand better what these methods do, I think will have an impact. Oh,
Okay.
do you agree?
Yeah, I do agree, and I'm glad you mentioned the statistics. I feel ashamed to not have thought of that because, yeah, a lot of the newer work that's going on with data and machine learning has statistics that plays a crucial role, and that's another part of the ecosystem. I mean, it's part of mathematics, but if I separate it from mathematics, that's also been ignored a little bit, but yet it's essential. And difficult questions. Yeah.
Thank you. Yes, another question or comment.
Paul, you were involved in the Exascale project for so many years in the US, and now since 2017 we have EuroHPC. My question is, have you or any in Exascale project in the US were consulted on your wisdom and experience gained over those years in creating EuroHPC program?
The answer is yes, informally. For a few years, I was invited informally, once a year to go to Brussels and have a 2-3 hour meeting with some people there. And as I say, this was not a formal US EU collaboration. It's just people that I knew and knew me. And so in that sense, I don't know whether I had an impact, but I gave some opinions. I have, in a more focused way, I've been on the scientific advisory board for the Barcelona Supercomputing Center for 10 years maybe. Now, we only meet every 3 years, so this is not very frequent, but I sometimes visit it at other times. And so I get a little bit of a view from them. I've occasionally talked to the Italian facility in Bologna, Sanzio. So nothing formal, but I have had some interactions. I have opinions, and I'll try to always say this is me, not the government speaking, because I'm not a government employee at this point. My feeling, and the same thing with Japan, by the way. So my feeling is that there is, at a high level, some convergence of what's necessary to do. In Japan and the European Union and in China, they're funding applications or planning to fund applications as well as the software, in some cases the hardware. So I think there's a bit of convergence to that as opposed to focusing only on new computer architectures and implementation technologies. Now, of course, once you actually want to implement the plan, then you have difficulties. I mean, the U.S. was really ready, again, in my opinion, in 2011, at the latest 2012, to have an exascale project. But it took 3 more years before all the pieces were put together. Some of it is funding, some of it is attitudes, and then finally there was a project. So it can take a while, and how you do it matters a lot as to whether you'll be successful.
And to my best knowledge, well, you were also in some years you've been collaborating with CERN in the field of high throughput computing, I believe. Yes.
Right. I retired from Caltech in 2002, and but then I was offered a position to advise the Inspector General of CERN on how to handle the data that the LHC would be producing. So this was 2002, so it was about 10 years before. And so I had already visited CERN a number of times and interacted with people and collaborated with people. But yeah, for that I had a 1-year appointment, and I drafted an approach to how to handle the data for LHC. Wrote a chapter in a book and presented it to CERN, and I think basically at a high level that's what was done. I was, in the 1990s, I was very interested in data already. I started a project called the Scalable I/O Initiative, which involved many people. I organized a symposium on what we would call big data in the year 2000, and so it was, just one of my side activities to worry about data. So that was my most focused involvement with CERN. Earlier than that, I also was involved with the EU on what became the EGI, the grid. That was, a colleague of mine and I went again to Brussels and said, here's an idea, and there was a tender, and then the European grid got started.
Thank you very much.
Thank you.